Alright, here we have lecture 2.2, which corresponds with section 3.1 of the textbook. So for unit 2, from this point forward, we'll be primarily focusing on contents from chapter 3 of the textbook, and it's this section where we introduce the function. One of the most important concepts in all of mathematics, actually. But before we get to functions, we need to define what a relation is. Now, a relation is a correspondence between two sets and can be defined as a set of ordered pairs. Now, this correspondence may be numerical in nature, it could be political in nature, it could be economic in nature, it could be random, could be subjective in nature. It's just some correspondence between two sets. And a set is just a collection of elements or objects. So here's an example of a relation. I could say Alaska corresponds to 1, Arizona corresponds to 8, California corresponds to 53, Florida corresponds to 25, and North Dakota corresponds to 1. So this is an example of a relation, and I can write this as a bunch of ordered pairs if I want. I could write Alaska, comma 1, because Alaska relates or corresponds to 1. I could write Arizona, comma 8. That ordered pair representing the relation between Arizona and the number 8. And then I could write California, comma 53, Florida, comma 25, and then the last one I'm going to go ahead and abbreviate it, North Dakota, comma 1. So there we have a set of ordered pairs. And this is a correspondence based on population, because each state's population determines the number of representatives. Now, the domain is the set of all first coordinates or inputs in the relation. So in that previous example, the domain would be the states Alaska, Arizona, California, Florida, North Dakota. So you can kind of think of the domain as your x values, because we associate the first coordinate in an ordered pair as the x coordinate. The range is the set of all second coordinates. So in that previous example, the range is all the numbers of representatives, 1, 8, 53, 25. You can view the range as the set of all y values. Now, a function is a very special type of relation in which every first coordinate or input corresponds to exactly one second coordinate or output. So in other words, an input cannot have multiple outputs. So each input has a singular output. So let us go ahead and look at this example at number 1. Is it a function? Well, 1 maps to A, 2 maps to B, 3 maps to 3, 3 also maps to D. So this is not a function because the input 3 has multiple outputs. 3 maps to C, but it also maps to D, so it's not a function. Now, this next example trips up a bunch of people. I say A maps to 1, B maps to 1, C maps to 1. This is a function. How many outputs does A have? Just 1. How many outputs does B have? Just 1. How many outputs does C have? Just 1. So what defines a function is every input has a singular output. We didn't say it has to be unique, just singular. So if we look at example number 3, this is a function because 5 has one output, 3 has one output, 7 has one output, whereas example 4 is not a function because input 5 corresponds to 1, but it also corresponds to 11. And so that's not a function because a singular input cannot have multiple outputs. Now, it's here we introduce function notation, so that what's written there is read f at x or f of x. We want to be very careful that we don't confuse function notation with multiplication. So it's kind of input-output. Whenever you see a function, function basically kind of behaves like this. I'll write it, let's see, right here. What a function does is you input an input and the function gives you an output. So one input gets you one output. That's what a function is. So if we go ahead and look at this example, number 1 is saying f at 3, what this is saying is input 3 into function f. So the function f is 2 times the input plus 1. So we set the input, which is represented by the letter x, to 1, and we get 7. So what that means is 3 corresponds to 7 for function f. For -5, that means we punch it in. So punch it into the function, and there we would get -9. So in this function, -5 maps to -9. And then lastly, we can input entire expressions. So here we're inputting the expression x minus 4. And we can go ahead and simplify that. And it simplifies to 2x minus 7. What we actually just did there is called composition of functions, but we'll talk more about that next week. Let's go ahead and look at this next example where we introduce our first piecewise function of the semester. Now, a piecewise function is a function defined in pieces. And some of you may recognize this type of function. This is the type of function you might use to program a computer to play blackjack. So this function says hit if the x value is below 17, stay if it's above or equal to 17. Right, so these functions are used throughout programming. So here's an example of a little bit of a function you might use to program a computer game to play blackjack. So g at 10. So remember, I can only have one output. It's either hit or stay. You can't have both. So we use hit if it's below 17. We use stay if it's above 17. The input is below 17, which means hit. G at 20, we're going to have an output of stay because the input is bigger than 17. Now here we need to be very careful on number 3. Note the little or equal to right there next to stay, so that's going to be the output there. And let's just do one more example. So I apologize for the handwriting here. We got h at 2. So we use the top expression. We use this expression, x squared minus x, if the input's below 3. If it's bigger than 3 or equal to it, we just output 5. So 2 is below 3, which means we're going to input it into the top expression, which is input squared minus input. So that would be 2 squared minus 2, which is, well, 2. If we input 100, that's just going to be 5. So this function will output 5 for any input that's above 3. And for -5, that's below 3, so we're going to use the top expression. So that's input squared minus input. So that's 25 plus 5, which gets us 30. Now, generally, when describing a function, we want to isolate the dependent variable, or what we call the output variable. This is called explicit form. So in other words, explicit form is getting y by itself. It's a standard practice to treat x as your independent variable, y as your dependent variable. So explicit form is just getting y by itself. And assuming y is a function of x, when you get y by itself, you can just replace the y with function notation. So what you can see here is just a bunch of implicit forms where we got y by itself. And as I've just mentioned, once y is by itself, assuming you have a singular output, you can switch it to function notation. So if we want to figure out if y is a function of x, we need to get y by itself. So here I can subtract x squared from both sides, then divide everything by 3. So you can see there's no funny business here. This is a function. If I input a number for x, a number squared plus 12 divided by 3 is a singular number. So input a number, you get a number. So that's a function. Now let's look at this. Let's get y by itself for number 2. So I'll begin by subtracting x squared from both sides. Now remember a square root property. If you square root both sides, you need to have a plus or minus. That plus or minus symbol immediately means that we do not have a function, because if I input a number for x, I'm going to get two different y values. Suppose I plug in 0 for x. Well, if I input 0 for x, I'm going to get an output of plus or minus 2. So that one input is getting me two separate outputs. That's not a function. Now let us focus on what we call real valued functions. So a real valued function is a function whose domain is the set of real numbers, and range is also a set of real numbers. So a real valued function is a strictly numerical function in which you input numbers and it outputs numbers. So if we're talking about a real valued function, we need to make sure that if we plug in a number, it puts out a number, and specifically a real number. Thus, we need to be concerned with division by zero and complex numbers. So the strategy with determining the domain of a real valued function, instead of focusing on what works, you want to focus on what doesn't work. So you want to figure out where the function fails to function. So if we look at this example 1, notice we're going to get division by 0 if x equals negative 2. If I plug in negative 2 into this f at x, I'm going to get negative 5 divided by 0, which is undefined. So we have a problem here. We have an input in which the function doesn't function. So that means we cannot have that input. It causes the function to crash and burn. So when we use an open circle for not included, we can pick any number we want so long as it's not negative 2, because negative 2 will cause division by 0. So the domain is negative infinity to negative 2, union negative 2 to infinity. You pick any number below negative 2, or pick any number above negative 2, but you can't pick negative 2 itself. Now some students will say, hey, well, what about 3? Can I input 3? Yeah, if you plug in 3, you get 0 divided by 5, which is, well, 0, and 0 is a real number. So we don't really care about zeros in the numerator. It's zeros in the denominator that are problematic. Now, in the case of number 2, this function g at x, which is equal to the square root of x plus 12, well, we don't want imaginary numbers. So imaginary or complex values will occur whenever you have a negative inside the square root. So that means whatever is inside that square root needs to stay non-negative. So thus we have an inequality. So clearly, if we want to keep negatives away from the interior of our square root, we just got to pick inputs bigger than or equal to 12. So if we were to put that on a number line, there's 12. You could pick 12, because 12 minus 12 is 0. Square root of 0 is 0. That's harmless. Or any number above 12. But the moment you pick a number below 12, you're going to have imaginary numbers. Like if we pick, say, 11, well, 11 minus 12 is going to be negative. Negative inside of a square root is imaginary. So the domain for this function is 12 to infinity. Alright, so as you can kind of see, what we're really focusing on is division by 0 and imaginary numbers, or what we call complex numbers. So, division by 0 occurs whenever you have, well, division by 0. Well, there's no division in this function, so that's not a problem. And remember, complex numbers come from square roots. Well, there's no square roots in this problem, so we don't have to worry about those either. So the domain of this function is all real numbers. You can plug in any number you want to f at x equals 2x minus 3. It will always work. Now, number 4 is a very different story. Here we have to worry about both. Note we have square roots and division by 0 are both possible. So division by 0 means whatever's in the denominator cannot equal 0. So we have x squared minus 25 can't be 0. So we go ahead and solve that. It'll factor to minus 5 plus 5. So in other words, x cannot equal 5 or x cannot equal negative 5, because those will cause division by 0. Now for complex numbers, we want whatever is inside the root to be above or equal to 0. So let's go ahead and solve that. I'll add 3 to both sides. Divide by a negative. Remember, when we divide by a negative, we have to flip the sign. So we need to pick numbers that are below negative 3. So let's go ahead and summarize all this on a number line. So we got negative 5 and positive 5. Both of those are open circle. Because we cannot include those numbers, they cause division by 0. We got negative 3, which is a closed dot, because we can input negative 3 if we so desire. So we can pick -3 or any numbers that are below -3. So there's our domain. So shading starts at -infinity until -5 parentheses, union -5 to -3, -3 getting a bracket. And there you have it. There's our domain of that function. So to summarize with domain of a real valued function, at least at this point in the semester, what we're primarily concerned with is division by 0 and imaginary numbers. We want to make sure we avoid any division by 0 and avoid complex numbers. And if we're avoiding those things, then our function should be good to go. So it's pretty clever what we're doing here to figure out what is allowed. We figure out what's not allowed. All right, well, keep up the hard work and have a wonderful day.